All right, I have right at 12 noon, so I think we will probably, if it's okay with you, Mahdi, go ahead and get started here shortly. We may have a few still logging in over the next few minutes. I want to welcome everybody to this month's seminar series with sponsorship from the UNH Center for Acoustic Research in Education. And I will mention that next month we'll have another speaker. We have scheduled both in November and December. And so I know many of you received reminder emails today from Jen or myself, and we'll continue to do that and make available on our CARE website both the schedule of speakers over the course of the fall and as we migrate into the spring semester. And we'll also be posting these great presentations on the website as well. Today we have speaking for us Dr. Mahdi Al Badrawi, and I want to tell you a little bit about his background, and then we'll kind of get started on today's talk. Mahdi did his bachelor's degree in electrical engineering, finishing in 2005 at the University of Baghdad. Did his master's of engineering in 2011 at the National University of Malaysia, and then came to UNH, where he finished a PhD in electrical and computer engineering in 2017. And since then, he's been a postdoc both at the Connectivity Research Center and CARE here at UNH, 2017 until 2020. And then in 2020, assumed his current position, the research assistant professor with CARE. And so Mahdi is really interested in signal processing. You'll hear a little bit about some of his work in that sphere today, but also signal decomposition, detection, estimation, and classification. And just kind of as a side note, a fun fact, Mahdi's a big fan of football. And by football, I really mean soccer, is what we refer to it here in the States. With no further ado, I'll introduce Mahdi in his talk titled Underwater Acoustic Analysis, the Power of Time Frequency Tools. And we appreciate you coming and joining us and providing a snapshot of your science today.
Thank you, Dan, very much. Thanks for the introduction, and thanks for the education committee in CARE to organize these events monthly. It's really a great opportunity to share our thoughts and ideas with other colleagues and students as well. So as the title implies, let me start first of all by a short background. So in 2017, I have done my PhD in electrical engineering. I have done works with detection, estimation, and other signal processing things related to wireless communication, biomedical signals, and other applications. I started my journey with underwater acoustics in 2017, and I had a collaboration with Jen and Tony from CARE and Kerry Seeger from Applied Science, and from that time I got involved in underwater acoustics. I got to know more this from 3 years now, and what I'm doing basically in this field is just applying signal processing techniques just to try to elevate some problems, solving some or maybe overcome some challenges that are really given in that field. So basically, we know that the data is really our link to understand and interpret any underlying features for a given phenomena. A general diagram for any of these links will be a sensor, and that sensor could record any phenomena like seismic, maybe wireless signals, and maybe acoustic, speech, whatever. And that could be one-dimensional recording, two-dimensional, three-dimensional, whatever dimensions we have. And basically, once we collect this data through those sensors, we have to really interpret and understand those data more, so we can really make a good benefit of those data. So that's where the signal processing comes, and that's where we can make really good advantage of a given signal processing techniques, or the innovative than maybe the new ones. So generally, the data really comes, let's say, clean from the source of the data, but there is always a channel where it's a medium where the data get, you know, impairments or maybe get distorted. And that's why we need, you know, a tool that really tell us really what was that data and what are really the features that really underlying in this data. So here's an, you know, instead of going very general, let's narrow it down to maybe acoustics, talk more specific about underwater acoustics. And we all know that, you know, the sensors there, they called hydrophones, and usually we have a sound pressure time series that are recorded. And here the analysis comes, you know, in three maybe different ways. Either we analyze the signal temporally, in time domain, spectrally, in frequency domain, or maybe in both together. That's what we call the time frequency analysis. So here we can see on the left, you know, panel, on the left figure, we can see a real data. And that data, if you take a look just, you know, visually, you see almost, you know, nothing. It's just a noise. Looks like a noise. But when you do a simple trick and a simple, you know, signal processing trick, you will find that there is really, oh wow, there is, you know, kind of, you know, something there. It could be, you know, maybe a call, animal call, or whatever, you know, a phenomena there. And that small trick, I didn't put that trick. I just want to tell you about it. It's really simply a second Laplacian derivative, or you could even do a first derivative to really, you know, unveil those, you know, hidden features in that, you know, noisy part of the signal. That can be done. This is done in time domain. This is temporal, you know, analysis. Or you could do that in frequency domain, where you could see that on the right side, the spectrogram, which is basically the representation of the short time Fourier transform. And it shows you as well that there are kind of two activities there, you know, as we show it really in using the second derivative. So that's kind of how we have, you know, these powerful tools to tell us really what's going on in any given, you know, recording or measurements, rather than, you know, seeing that, you know, noise on the left side in the beginning. So that's just kind of a fun example to how these, you know, tools are really important and useful. So 3 problems to discuss in this seminar. So I will go, you know, through some detection things and work a little bit on the classification and separation. All of these will be for underwater acoustics if you are interested. So, and all of these, you know, part of my, you know, past research in the past 3 years. And there is more research, but this is what I tried really to highlight in this, you know, short seminar. So for the detection side, I promised myself when I was, you know, preparing these slides just to keep it, you know, with as many pictures as possible, because when I'm, you know, watching any presentation, I really would like to see less text, so I try really to make my promise happening through. So, you know, signal detection is basically involved of differentiation of the you know, some useful, good features, meaningful features from random, you know, patterns such as noise or clutter in active sound or whatever. So here I'm showing you another example of data measurement or whatever, some data sample. All the pictures you see are real data really. So this is another sample of, you know, 5 seconds, and you could see from the spectrogram that we have. I don't know if you see my cursor or not, but I'm trying to pointing here on this, you know, kind of call. This is animal call. So if you are really interested in this and doing a detection for this specific thing, you will find that, yeah, thank you, Lida. So you will find this is, there is a couple ways to do it. It's really obvious from time domain that there is something here. But the reason why I put this picture here is to show you, what if someone really interested in seeing, you know, what are these really lines? These are kind of electrical noise bands. So if someone really want to detect these because they are interested in maybe measuring the noise level and somehow for some frequency. So how can we detect these really? So again, I put less text. I will just try to explain this, orally. So we cannot see anything from here. We could see it from the spectrogram, but how can we make a kind of automatic detection for these if we want to? Yes, visually we can see it here in the spectrogram, but one of the ways to do this is really use the power of what is called the fourth moment, which is something called spectral cartouches. And spectral cartouches basically you will find a bunch of frequencies on the frequency axis, which is here now. But don't worry about this figure. I'll explain this figure later. This is not what I'm trying to say here. And you will see those frequencies will represent this, kind of marine and mammal who make this call over all the frequency band. So sorry. Of all the frequency band, but really we are interested in these bands. So how can we get these bands? If we understand more about signal processing tools, so we will know that the cortosis is a great tool to detect the non-stationarity of the signal, and this is now the non-stationarity. And at the same time, the cortosis tool will give you kind of negative values for when you have kind of stationary tone, let's say a tone that's really just happening, constantly over the time. And that's if you now let's move to the next figure, which is on the right hand side. You notice that what I have done here simply, very simple technique. I found these negative values. I just took the absolute of those negative values, then just show them as a positive, so you can visualize them easily. And that's why I put here the negative spectral cortex, because these values have been negative, but just for the sake of detection, I just took the magnitude of those, make them kind of positive, let's say, take an absolute, and you could see here easily that there is the almost 5,000K, which is here. You find the 12,000K, which is this. You see the 25,000 and the 40,000. So in a nutshell, what I'm trying to say here is, if you are interested in either stationary or non-stationary tones, you could find them really easily by playing with the available signal processing tools. And one of them now was the spectral cortex, which is really very powerful. Now, very simple threshold here, you could automatically isolate these and say I have a contribution from in the 25,000 hertz and whatever and say 40 and so on. So this is another example of another set of data where we use different statistical different signal processing tool, which is really called a Centroid. So we see here small animal activity and below, let's say 2 kHz, and we've been able really to detect that. Let's just remind ourselves that I'm speaking of detection now. So that's called the brightness, how bright the spectrogram is and the time of frequency. And the Centroids really are really great tools really to detect these, let's say hidden. Oh, that's not that hidden really now in this example. But another example, another more severe example with DOS and ARMS, you will find this is really a quite useful tool, which is really the spectral Centroid. Here again, we are using the spectrogram, the FFT spectrogram, to detect the activity of that, of that data sample. So now, again, the spectrograms are really great. They are being used from long time, and yes, there have been kind of improvements to make them really looks great more. But what if we can find really a way to represent this data in more neat way, in more, let's say, with less noise, with less of these colors? Why this is important? This is very important if you apply these, spectrograms for, let's say, machine learning or the most, contemporary things, the deep learning things. So when you need really kind of good pictures of your audio files or let's say acoustic files. So here now there comes the role of what is called, I mean, my group and I, we call, let's say personally, EMDgram, which is kind of modification of spectrogram. I don't know if this is make any sense for people in the field, but this is just a name. We call it EMDgram. So the EMDgram basically, as you can see, it's the same as the spectrogram, but we got rid of all these, let's say noise. If there's a, small, let's say these colors, maybe the yellow ones are really, background noise. There's no background noise, and we got only the good thing, the good part of the signal, which is that animal call. I'm not expert in these animal calls, so maybe Jen or maybe Tony, Dan can help you with these. So anyways, so let's see what's really the EMD. So I'm really just trying today to talk a little bit about the EMD, which is really quite useful tool as a time frequency thing, So the empirical mode decomposition, or EMD, is a decomposition tool that really breaks down the signal into finite number of components. So let's say you have a multi-component signal, multi-sources coming together. The EMD is really able to differentiate these based on their frequency content. If they are overlapping in frequency, EMD really will suffer, and get them out of the overlap. This is a very common problem. And the output of the EMD, which we said is a really finite, set of components called the intrinsic mode functions, in which each mode is really intrinsic from the others. So this is a good, really, comparison for anyone interested in signal processing to see where is the EMD in contrast to the Fourier wavelet, the well-known, time frequency analysis wavelet transform as well, which is really a great tool. So here's, a couple of criteria that the author of the, let's say, the inventor or whatever, the author of the EMD just put in his, book. So EMD is, they called here Hilbert, referring to the mathematician, Hilbert, and the guy who, who just, proposed the EMD, his name is, Norton Wang. Anyways, so Hilbert refers here to the EMD or whatever, the representation of the EMD on the 2D scale. So the EMD or the Hilbert is really adaptive. It's differentiation, mathematically it's a differentiation operation. It's energy, time, frequency, again, a representation of the signal. It works these are the strength of the EMD. It works with nonlinear, non-stationary signals, where the wavelet, you need to customize this. It's great for feature extraction, and the theoretical is still empirical because it's a kind of algorithmic, kind of tool. So it's unlike the Fourier where you have these, bases are known priori, like the wavelet as well, where we have the mother wavelets, like Davachi's, for example. So the Hilbert or the EMD, called adaptive because simply this is really extracting the basis of the signal from the signal itself. So there is no need to set any kind of sinusoidal things like a Fourier or maybe mother wavelets like a wavelet, transform. This is only extracting its basis from the signal itself. Another good figure to show you here is really where the EMD, located in contrast with other, algorithms such as the empirical orthogonal function, which is basically based on the SVD things, which is the singular value decomposition. Wavelet is here. Wavelet is really robust, but the adaptivity is really kind of less. The EMD, simply again, the adaptivity is referred to setting the basis of the decomposition a priori. Here we are doing that posteriori, so it's really happening from the signal itself. Fourier transform, WB distribution as well, they are really similar because they are kind of overlapping. They're holding the same kind of principles. So this is good graph kind of to show you, but again, you see it's more complex. That's one of the drawbacks of the EMD, at least the old version of the EMD. That's because Norton Wang, proposed this EMD in 1998. So that's quite a time now. Simply just, to give you a short, maybe explanation of how the EMD really works, maybe because simply again, the text will not help. Pictures will usually help people visualize things. Let's say we have this, very simple signal, which is composed of different sinusoidals. EMD simply works by finding these peaks here, These we call these maxima, and we're finding the minima, the other properties. Okay, then we connect them like this. So you see the green line is the envelope in the upper of that data, which is in blue. The data is in blue, and the lower is really the lower envelope. Then simply, as simple as taking the mean of these two envelopes, you get this mean in red. So you subtract this mean from the original signal, and you will get, so you will get, you will pass the first sifting iteration. You will do that over and over again based on some stoppage criteria. Then you get your IMFs. So these are really amplitude modulated or frequency modulated components, IMFs. I didn't put much figures of these, because I tried just to keep it, as neat as possible. So how we get these figures, these nice, I don't know what is this. This is maybe purple, dark blue with a white, nice white background after getting rid of all the noise and electrical noise, let's say. So simply this is called Hilbert-Lewin transform, formerly HHT, and we would like to name it Empground. So it's a very useful tool for nonlinear, non-stationary, signals. So simply you are decomposing the data that you have in time domain into a set of IMFs. You apply or compute the analytical Hilbert, signal for each IMF. You get amplitude and phase. Then you calculate simply the instantaneous energy and frequency, and the HHT or the Hilbert transform will show you those energies in these colors over this time for those frequencies. I would like to emphasize that if you look at this, spectrogram, you will see that this animal make kind of discontinuous sounds, and this seems to be continuous. Yes, that's the old EMD version. Newest versions will show you those discontinuities, as well, likely similar to the spectrogram, with the advantage of having these really clear, almost because you have all these values, and these, white space are really zeros, kind of. So this is a sparse kind of representation of the spectrogram. So let's show this example now. This is real data from, if I recall, this is from the CTVTO data, and we have low sampling rate here. So I just try to zoom on this 1 minute sample. I just show you here, there is two activities happening here, or let's say of that mammal. Regardless what is this, I don't know what is this. But anyways, so you have two activities apart in time, kind of small time. This is their spectrogram. Yes, there is kind of discontinuities here again. The EMD show you this as a one piece, or maybe if you focus more there, you could see maybe there's some colors there. This is the energies that's really focused there. But I just keep it as simple original EMD. These are not newer EMD, versions. And if we zoom more, EMD is really able to show you, these two activities in time domain separated well in time domain and in frequency as well. So that's really kind of example of when you have low sampling rate. The other pictures I showed you before, we had really high sampling rate. That was the pictures really kind of was the pictures were very clear. So I will present two case studies here, real things, real based on the publications we had before. So first of all, involving EMD detector, because we just explained the EMD and how it's really powerful thing. So we had 5 seconds of data that has really different kind of activities: underwater flow, beluga whale, sperm whale, plaques, morning chain. So all these are really different activities from different sources. Simply what we have done is really decomposing the time domain of this signal. I'm showing you the spectrogram because it's really you could really at least visualize what's going on. This time domain will not show you a lot. So we have applied EMD on the time domain version of this data sample. We got these IMFs. these are not really IMFs. IMFs usually looks like a time domain and plus and minus things, you know, positive and negatives. What we have done, we applied a Hilbert envelope that will really kill all that unwanted noise and show you only the you know, these features, which is really the peaks. Then simply these are IMF 1, 2, 3, 4 till 8, and there is more IMFs. Maybe if you could set this for more IMFs, but we notice that these are really enough IMFs to extract all the necessary features. You could say that you could see here simply that the first IMF we extracted these clicks in the first and second, and then third as well. You could see this in the third, but these are really kind of less power than these. These have a higher power. We extracted the morning chain in the first IMF only, and we extracted the clicks in the first and the second and the third. For the Beluga whale, we've been able really to, this is Beluga star digital here, but the most contributions happening in 2 and 3 and 4, and 5 as well, but 5 is kind of, I will show later, it's less. And that was the first step. So we really detected, or maybe we really decomposed this sample data, which has really 4 different activities into these 8, components. The next step was really to, I'll back here a little. So we really choose which are really the best IMFs out of these, because you see here simply this is almost noise, or maybe something that's really meaningless. So we apply another tool of the signal processing toolbox, which is the correlation. So we correlated each consecutive IMFs. This is the IMF 1 with 2, this is IMF 2 with 3, this is the correlation of IMF 3 with 4, and so on. So we just collected the first 5 IMFs. The reason I say 5 because this is 4 and 5, right? So the first 5 IMFs, and we done a reconstruction. So we add them, we sum them all together to get this nice, 1D figure. That's really the normalized amplitude of the activities over the time. So then we set a threshold there, just to to say, okay, where we can really track these points. The threshold helped us really to detect, or maybe to localize these activities. So simply, if I find the point here, and the point here, that's the activity that's related to the maybe underwater ball. This is for Beluga, this is for the maybe for the morning chain, and so on and so forth. So after detecting these sounds, that's really sensitive. Okay. After detecting these sounds, it's now the time to move to the next segment of our presentation, which is the classification. So we need really to know which one is which one, and which which detected period was belong to which animal, which activity. So here's the classification coming. We use the same EMD, the same outputs. So the classification by the EMD was an attempt really to provide alternative way other than the machine learning techniques. And this can be seen as an approach to tag each marine mammal based on its acoustic fingerprint. Honestly, it's a really challenging task. We had success in some animals, and it was really difficult for other animals, and that's really ongoing research till this moment. So simply, we take that's time period, and we calculate the power over that small time period over all IMFs. So the highest 2 powers are really the significant IMFs of that activity. Now, if you see here, so this is the relative period that we cut. So that's for the I remember that was underwater, right? Let's see. That's for the underwater blow. So for the underwater, so we have these. So if you look at the table here, so for the underwater blow, we just nominated 2 identities, 3 and 4. So that means whenever we have IMFs 3 and 4 happening, for that period of time, that's a beluga, that's underwater blow, and so on and so forth for the beluga, whale vessels, spermal clicks, morning chain always happening in 1 and 2. So these are kind of fingerprints for each activity. The third thing, just to discuss today is the separation or clustering. So when you do sound source separation, this is a quite important problem because we know that we have, several good, clustering techniques or source separation techniques, PCA, ICA, as well as the non-negative metrics. This is the NNMF, which is the non-negative metrics factorization, K-means clustering. All these are really good techniques, but each one of them has its own pros and cons. So in the second case study, which is our latest publication, we done a work on a data coming from a bearing stake exercise that was recorded in 1977. So the challenge there, we had really few days of data, and we couldn't really do kind of the normal analysis that's usually people conduct on for long-term analysis of these data. So we had very short time to analyze and say make conclusions about the ocean status at that time. So this is a table explaining we had 3 sites and the coordination of each site, the depth and the recording period, and the depth of the hydrophones. Basically, what we have done here in this research is really we use the power again. So I focused in this research about using the normal FFT. This work can be expanded to use the EMDgram as well, but this is using only the spectrograms as a powerful time frequency tool. So simply what we have done, let me open this. This seems like kind of scary, but this is really very simple, a use of the available signal processing tools. Sometimes you just put them in a new way that's really show you a great results. So we started by segmenting the data. We took like 1 minute each 10 minutes. So, and we created a data set of that. So each segment, we call the segment, was 60 seconds in length. And simply we just converted each of these segments here in this, highlighted red block into using the short time Fourier transform into a matrices. So each one vector here had been transformed to a matrix. And then simply our approach was to cross-correlate, let's say we start with segment 1, we just start randomly. Assume we start with with segment 1. So we cross-correlate segment 1 with all the the matrices or the representations of other segments. Okay, so that's really resulted in a big a 3D matrix, and that matrix really had each one of these matrices has the cross correlation of this one, okay, with the other segments in the entire data set. Then we simply, what we have done is picking the maximum value of each of these matrices. Then we sort those maximum values ascendingly. So with doing that, we have done kind of a dimensionality reduction and kind of feature extraction. The feature was the maximum, very simple feature, but it was it's yet powerful. So now this is basically the sorting of these. We just put it in a matrix in a vector called CM for short. And what's happening really in CM is these are the sorted maximum values of cross-correlating one reference segment with the entire data set. Now here's the tricky thing. So if that reference segment was just a noise, was just ambient noise, we know that the ambient noise doesn't have correlation even with other ambient noise. So that means you will have a kind of a pattern similar to this, in which you will not have any significant changes in the indices here, in the correlation indices, coefficients, sorry. Then, in case you just you do that over a while loop. Let's say you went to the next segment. Let's say you had something that's really has some structure, and that structure will have maybe another siblings, let's say, in the data set. So you will have this kind of presentation in which those similar segments will have a correlation, right? So they are correlated. So we group them based on this threshold. We have two thresholds here. So if you have at least one threshold that's happening, in this area, or the second half of the indices, so you will say that from this and on, all these indices will belong to the same source, because they are carrying the same, correlation coefficient strength. So simply we done this simple hypothesis. If at least one of these two thresholds happening in the upper part of the correlation indices, then this is a source, and if not, this is just ambient noise. We've done further clustering here, just to sift more the more ambient noise from the ship noise only. The paper is available online if anyone is really interested in reading that paper. It's Bering Mistake 1977. So simply, this is the third step. So I don't really to go in depth with this, but it's really explained well in the paper itself. We have found, based on this method, that there is 4 groups of data. Actually, there have been 5 groups. The other group was just the ambient noise segments. So this can be considered as a group. So simply what we have done, instead of having 1,004, let's say 1,000 or 2,000 minutes, and each minute represents something. So we have now a group, 5 groups. Each group, maybe one group maybe has 700 minutes, the other have 300, maybe someone has 50 only. So we group those, minutes or segments into 5 groups. That's kind of great, complexity reduction for the operator. And each one of these really has, let's say, source A, for example, consists of broadband signal, particles or plankton, and so on and so forth. So we, with help of Jen, from Jen, she's been able really to classify these. So simply, the statistical, the signal power processing tools will separate these as a groups, and the operator, in my case was Jennifer, she did say, okay, this group, because this is the main, this is the, let's say we had 300 of these, so just look at the 1 or 2 of them, because they are all, happening in the same cluster. So we could say this is, this is that, and this is, another source or whatever, and so on and so forth. So we've been able really to do these proportional things. So we say that we have 34% coming from the, let's say, source C, which is ship noise, and the ambient in site B was really a big chunk, same for site 4. And that was a really quite useful tool to use for clustering, other than using the PCA or whatever other things, or maybe techniques that are really available. Basically, and simply, it really depends on the cross-correlating the pictures of the spectrograms with each other, and using simple thresholds based on the changing points after doing sorting. That was really important piece of contribution. The sorting was really, although it's really straightforward things, but really was really useful. So as a conclusion, I would like to say that signal processing tools are really useful tools if you sometimes put them in right order, let's say. So we haven't invented the wheel, we haven't reinvented the wheel, but you just use a couple of this big toolbox library of signal processing tools, just in kind of new way. So with that, I think I'm done, and I'm happy really to have you, maybe if you have questions, or maybe open the discussion for this presentation. Thank you.
Thank you, Mahdi. I appreciate you sharing these different models with us today. I think what we'll do at this point, we're doing really good on time, is open it up to questions. So from across the audience, if you have a question that you'd like to either turn your mic on and ask Mahdi, or if you want to put it in the chat box, maybe we can monitor that as well. I did have one question, Mahdi, about, I think the examples that you were showing had pretty a high ratio of energy, the signal to noise. Have you seen some success using this technique when you have signals really embedded within a noisy recording?
Yeah, that's right. Yeah, for at least for this, you mean the clustering, the last example?
Mm-hmm.
Yeah, that works really well with the bearing stick, where we had like a sample rate of 2,400 hertz. Mm-hmm. So it works well. But I'm telling you, if you just go down, like using maybe CTBTO of 250, that's not gonna work. So we could say this is one of the disadvantages of this method, is really you need a very clear spectrogram. So you need very good spectrogram. Maybe right. If you use EMDgram, which is really less noisy than the FFTgram, then you might. I haven't tried really myself because I was focusing on this STFT because it's been really clear for me to use them. Using another data with less sample rate, no, this is not gonna work.
Right. Thank you. Other questions from our audience today? For Mahdi. When I'm watching the examples that you gave, and I appreciate providing those, Mahdi. I'm a terrestrial bioacoustics person, so of course I'm instantly shifting this to thinking about how or whether we could use the same approach. I'm quite sure you'll weigh in on this, but for terrestrial recordings, where maybe we're seeking to classify particular signatures in these soundscapes.
Yeah, that's really can be, again, signal processing tools are not really limited to any application, a specific application. So I believe, although the channel really in underwater is different, kind of, and for sure different than terrestrial, but I mean, I'm quite sure there is good tricks in signal processing toolbox to really handle those problems that you guys having in terrestrials.
That sounds like a challenge that we need to accept, I think. So.
Yeah, I will take
it. All right, we have another question in chat from Chin Ming, asking, is there a paper that she can refer to about today's talk and the technique that's used? Can you cite a paper for that?
Yeah. This technique is really just published like a couple days ago in JASA EL. Yeah. So and the paper, if you just wanna, I don't know, maybe I will share it in the chat itself. Let's see. So it's called bearing stakes exercise 1977. Where are the notes? Let's see. How can I share this?
If you click on on the chat window, you can type in the reference to it.
Yeah. So yeah, chat window. Yeah, here we go. Yeah, here's the. So I just put it in the chat here for everyone.
All right, very good. Thank you.
Yeah. Let's see. So that's the paper that I refer to now.
Thanks for posting that, Mahdi. I also have a question from Bruce Martin.
Yeah.
about EMD and classification, that the EMD generates its own basis functions and weights to go with them. If the bases aren't defined, what do you compare the bases to for purposes of classification?
Could you please repeat this? I could.
Bruce, would you like to ask that?
Well,
Are you? Yep.
Looks like I can unmute. I didn't think I could.
Yeah. Hi, Bruce.
Really interesting, Mahdi. I really enjoyed this, but I just was confused about classification with the EMD.
Yeah.
So if I followed what you're saying, EMD is going to make its own set of basis functions for each data sample that you put into it. So then the question is, how do you classify with those results? Because you won't get, like, there won't be a template for a humpback, or there won't be a template for a sperm whale.
Yeah, that's right.
Yeah, there'll be a distinguishing of there's some energy here that you should look at, but I don't see how, I don't follow the classification step.
Yeah. Sorry, maybe I won't maybe quite explain this because of the maybe time and a couple of topics there. So simply what we are doing here. So usually what people doing in classification in underwater acoustics, they are starting looking at the spectrograms and they say, okay, we have this and that, then they throw it maybe in machine learning or deep learning techniques, right? So that's what we're doing. And in our way, we do that in inversely. So what we are doing, let's say I'm identifying these identities, then the operator will come and say, okay, I noticed that whenever we have beluga whale, it's happening in 3 and 4 IMFs, in IMF number 3 and 4. So that means whenever we have an identity of 3 and 4, that's beluga now, beluga whale. So we do that later after getting the IMFs or after getting the IMFs identities. So this method works really, and it's really based on some published work in just a journal. So it's worked really well with some animals, and it didn't work well with other animals. And we had as well, if you look at the, let me share this again. Yeah. So if you look at the table, here's the table. If you look at the table here, so you will find that here. So you'll find that there is maybe a couple, let's say the AWCPs and the morning chain have the same identity. So that's a fail by the algorithm to show you two different things as a one identity, as a one classification, output. So this is, again, as I said, this is an ongoing project funded now by ONR, just to expand this work and understand if we can find an alternative way to the machine learning, techniques that are available nowadays. So I don't know if I answered the question, Bruce, or not. So
you might have, and I'm just being slow. So what I'm getting here is, like, what I understand is say you're IMF1.
Yeah.
IMF1 picked up this. I think you said they're sperm whale clicks primarily.
Yeah.
And then 2's got some of them, and 3's got some of them. But if there's no sperm whale clicks, or if the sperm whale clicks occurred at a different time, then the peaks in IMF1 are going to show up at a different time. So it's not a reliable pattern that can be used.
No.
To say,
it's not dependent. Sorry for interruption. It's not dependent on time at all. It's depend on the energy of anyone. I showed this time here just to tell you that we found the energy of that time segment of that specific time, just to work on a single animal. This animal could happen in any time during this 5 seconds. It doesn't matter. Yeah, it's kind of frequency content classifier. It's not time content. Yeah.
Okay. I think I follow a bit better. Okay. Yeah. Can you change the frequency bands of the IMFs to get better frequency parsing so that you could have better distinguishing of what the source is?
Yeah. Yes. I mean, that's a good question, really. So with the conventional traditional EMD that I just explained, you could do that with one really assumption, just asking the algorithm to give you more IMFs. That's really it's really a dyadic filter, right? It's a kind of filter bank, similar to the gamma tone. So, but if with newer versions of EMD, something like there is something called variational mode decomposition. That variational mode decomposition will work really much better than this in let's say sub-banding the total band into different bandwidths. You can control this for sure. Yeah.
Okay, I'll stop babbling now. Thanks.
Yeah, thank you.
Thanks for the questions, Bruce. Do we have any other questions from the audience today for Mahdi on his technique that he shared with us today? If not, I have posted in chat the information for next month's seminar. We have a speaker from Oklahoma State University, the Mechanical and Aerospace Engineering group there, who's using kind of a similar approach to what Mahdi's talked about today, but using sound detection and classification to search for a tornado. So it'll be an interesting comparison between our marine bioacoustics talk today that Mahdi shared with us with the hunt for tornadoes. So Mahdi, we appreciate you coming today and sharing your science with us. We look forward to hearing more about your work in the coming days, weeks, and years as a member of the CARE team. And we appreciate everybody who's been online today with us. I think I counted 31 at one point logged on for the seminar. And we look forward to seeing you all again next month on November 10th. So appreciate your continued support of our seminar series.